I'd like to welcome Guido Tosolin to the stage. Guido represents IDIADA, and VI Grade and IDIADA have had a very long, fruitful relationship with each other. In fact, I think everybody in this room who has driven a simulator at one point or another has said, hey, I want to drive the IDIADA ride roads. So today, to represent them and to give a great presentation, we'd like to welcome Guido Tosolin to talk about the development of chassis algorithms to enhance model development and rear-wheel steering. So Guido, stage is yours.
Hello, my name is Guido Tosolin. I am responsible for vehicle dynamics development in IDIADA. For those of you who don't know IDIADA very well, we are an engineering company which provides services to the automotive industry in the fields of complete vehicle development and engineering in all different functional domains. We also are a very important testing and validation center, and we also provide support for homologations worldwide. So we are around 3,000 professionals, and we are located in 22 different countries, and our main headquarters is in Spain. In Spain, we also have our quite famous proving ground, and we have our DIM 250. We have another DIM 250 also in China that we run in collaboration with VI Grade. Okay, that's enough for the introduction, so I'd like to go now through the presentation of today, which is about one issue that we have in today's industry. It's not an issue, it's actually a big opportunity, but also sets some challenges for us. So it's the fact that vehicles have an increasing number of electronic chassis control systems, and we have sort of a headache trying to integrate all these systems together, and also within the passive chassis components. So this challenge is made even bigger by the fact that very often when we start developing a new vehicle or a new vehicle platform, we miss models of these systems. So we don't have the information from the suppliers in order to integrate these systems in the early stages. And so this means that it's quite difficult to plan a comprehensive strategy for target cascading where we can allocate specific performance components to the passive chassis, the kinematics, the compliance, taking into account that the vehicle will actually have a number of different electronic chassis control systems. And there is also another limitation, which is the fact that if we are missing these systems, we are also missing them for digital twins. What is a digital twin? So nowadays, we work on the simulators, similarly to what we used to do and what we're still doing in the proving ground. And when we are doing development, we always want to have a reference car to compare and to understand where is the gap versus our best competition. So a digital twin represents exactly this benchmark, but translated into the virtual environment and especially in the driving simulator. Of course, if the vehicle model that we are generating of the benchmark vehicle will have certain active systems, we need to have those systems integrated in the digital twin. So the solution we have been working on in the last years with a number of customers is to develop what we call behavioral models, which means a library of models of the most widely adopted chassis control systems with the purpose of having them available for early stage development and for digital twins. And the company we have been working the most in this domain is Nissan, with which we have started to collaborate in this domain in 2017, and we have elaborated a number of different projects with them in this area. And today's project is exactly about this sort of process. So I'm going to present the latest study we have done together in which we had 3 different main objectives. So the one objective was to develop a digital twin of a benchmark vehicle that could be used as a reference in the driving simulator. The second objective was to generate a rear wheel steering logic that would be representative of the actual behavior of the rear wheel steering installed in the benchmark car. And the third is to have the possibility to make this logic very tunable so that we can then use it in the early stages of development for new programs, and we can have different sort of behaviors out of it. So the activities we have gone through in the project are the testing, extensive testing of this benchmark vehicle, then the generation of a passive model and the generation of an initial concept of the logic of the control rear wheel steering, and then the integration on the driving simulator. So the outcome of this activity is the fact that we have enough data for model building and model validation. We have a model of the passive vehicle with the integrated rear wheel steering, and in the driving simulator we will go through a complete validation of the model, both at objective level and at subjective level. Okay, so let's go through the process of model generation and validation. So typically when we want to generate a digital twin of a specific vehicle, we need to do a lot of testing. So luckily in IDIADA we have all the facilities to generate enough data to supply all the different parameters that we need to input in the model. And this is relatively straightforward and well-established process when it's the passive vehicle models. So typically we will generate tire models using, in our case, a tire tire trailer. Then we will have testing done on the KNC rig to generate the multidimensional suspension mapping and also obtain properties of components such as the bump stops, the springs, the anti-roll bars, etc. Then with full vehicle testing, we will generate simplified data for the powertrain and for the brakes, and also for the aerodynamics, where we combine this data with some, let's say, reference for the kind of vehicle category. And then last, but not least, we also measure the vehicle on a specific bench to have the complete inertia tensor and the COG position of this vehicle. So all these data are introduced in real time. The process is quite automated, so it's quite a standard activity. So the difficulty comes when we need to generate on top of this, and we need to integrate also a chassis control system. So in this case, we need to do some advanced testing in order to make a characterization of the system, in this case for the rear wheel steering. So the strategy here is to have a specific set of maneuvers which are planned in order to excite the system in many different operating domains. This means we will realize typically open loop maneuvers, but in a wide range of speeds and conditions, and we'll also generate data from normal driving or driving on a handling circuit, etc. So in this case, what we want to have is the actuation of the system in a wide enough range of scenarios. And then what we need to do is to instrument the vehicle not only with the standard complete vehicle measurement devices, but also having specific instrumentation applied in the actuator which is under investigation. So in this case, was relatively simple. Other cases are more complicated. In this case, we just introduced a wire sensor in the rear rack. Okay. So out of this specific measurement and all this set of different measurements, we generate this sort of data where we have the rack displacement and its evolution in different testing conditions. So in this case, you can see from the steady state cornering, for instance, as just an example, we can see how the rack actuation changes very much, increasing the speed, of course, moving from an out of phase to an in phase actuation, increasing the speed. And also you can see different sort of actuations occurring during a lap on the dry handling, whether we are driving relatively slow or we are driving more at the limit of the vehicle. You can see the rack will change its behavior. So once we have collected all this data, the process is similar to this. So we, of course, from the state-of-the-art and analysis of the test data, we will have an initial logic that we integrate in the passive vehicle. And then we'll all compare offline simulation, and we will try to achieve the best level of maximum level of correlation that we can. And whenever we need to adjust the model or adjust the tuning parameters of the correlation, we'll do that until we get enough correlation for all the offline maneuvers. And then we will also run sessions at the DIM with expert drivers who have driven the real car until we get a behavior which also subjectively feel the same, because there are many points, of course, that cannot be measured completely with the offline maneuvers. So the variation and the kind of style of driving can influence, and we want to cover all these aspects as well. And again, in this driving simulator session, we may tune again and modify the logic until the point when we are quite happy with the model and we consider it correlated. So specifically, the rear wheel steering logic that we generated is relatively simple in the sense that it captures the typical behavior and the typical objectives of a rear wheel steering. So it enhances agility at low speed and enhances stability at higher speed. But it's also a little bit more complicated than this, because depending on how the driving is, the driver is driving, so it's not only based on speed, it's based on a number of the other different factors. So finally, the logic that we have developed is mostly based on two components. We have a feed-forward controller, which will operate based on a yaw rate reference and on a reverse model of the vehicle, and we have a feedback component. And based on the different applications and based on the vehicle we are trying to match, we will activate and tune the logic and maybe deactivate certain parts of it. The logic also has a wide range of tuning parameters that we can use in order to modify its actuation. So we can operate mostly on the yaw rate reference gain, on the yaw rate reference gain on the yaw rate reference in terms of the linear range of the yaw rate generator, and also, of course, on the parameters of the feedback controller. So the results can be observed in this slide. So in this slide, you can see the measurement data. In this case, it's a steady state cornering constant speed maneuver, in which you can see the level of correlation that can be achieved when the logic is not working, so the simulation passive in this case, so the red curve. And you can see that when the rear wheel steering is activated, then the correlation level increases significantly as expected. So especially for the low speed maneuvers, you can really see that the rear rack is behaving in a similar way as in the real vehicle, and that as a consequence we can have a much better correlation in terms of lateral acceleration response and side slip angle response versus lateral acceleration. So you can also see how this changes with evolution with speed at 30 kph or 60 kph. And then, as an example of the effectiveness of the system running on the simulator, you can see here the yaw rate and the rear toe, so which is connected with the rear rack displacement that is obtained in a lap in our dry handling running on the DIM, and you can see the impact that the rear wheel steering will have on this vehicle. So this is how we typically would validate such a model in order to make it then available for, as we said, benchmarking in the driving simulator, but also as a starting point logic for new development. So the conclusions, at the end of the project, we were able to have a complete digital twin of the competitor, which also included the rear wheel steering logic, and this logic has been already applied both for benchmarking and for early stage development of new Nissan products. The next step that we are following, this is an activity that we have been working on for several years. So this was one example, and we keep expanding the library of active chassis control systems, because one main interest for us is to be able to actually combine together many of them and study strategies to integrate them better with integrated chassis control logics, etc. So, and what we're also working on is to develop a very systematic and almost automated parameter tuning, so that from the test data with an existing logic we can more effectively and more efficiently adapt the logic to the specific target vehicle, and that is especially interesting for the digital twin model case. Okay, so thanks. This is the end of my presentation. If you have any question, I'll be happy to try to answer.
Thank you very much, Guido. We appreciate your time and energy into that presentation. Any questions for Guido at this point?
Thank you very much. Yep. So great presentation. The question that I have, the way that I understand the process, it's really you're feeding the parameters to your behavioral controller there using test-based data, and you mentioned that you analyze different scenarios to expose different conditions so that you can get that right. Do you make any special consideration for environmental or test equipment noise sources for this feeding?
Well, we in this case, the measurement has been done mostly on dry roads, okay, and in stable conditions. So in some other cases, for other controllers, we have also tested the vehicle in different mu conditions. So that is mostly the case for instance, all-wheel drive logic or the torque vectoring, in which we make use of a wider range of scenarios also based on high and low mu. In this case, we focus more on the high mu because that was the request for this project, but definitely the conditions and the road conditions are very, very important. In that case, we will need also to have a specific effort to model properly the tire model in these different conditions.
Any other questions? Yes.
Great presentation. Do you think you'd be able to use the same approach for semi-active dampers, or is that kind of outside of the too much work to create the model to then correlate?
No, I think the same approach could also be applied for semi-active dampers. We are actually building the basic logic of a semi-active damper. The difficulty there, I think it's more on having proper testing data as well. So of course the model of a damper is the model of the physical model of a damper is much more complex than the model of a rack steering. So that's also another level of difficulty. But I think the same approach in principle could be applied as well. So when we think of it, and we have been thinking of it together with the customer, is also the testing side, because of course it's very easy to measure just the behavior of the rear rack or even the torque transmitted to the wheels from the motors. We normally do that with strain gauges installed on the drive shafts, so to get this data. And in this case, the measuring of the actuation of the component becomes much more complicated. But there are ways to do it, but it's much more complicated.
Separate out the control command and the actuator, or more of your focus is at a characterization of the ECU and the actuator together in the response? So like if you're characterizing the rear rack, you're getting a response of both the commanded input and how the actuator acts to the commanded input.
Yeah. So in this case, we are focusing more on the final output. So we call it behavioral model because it does not take into account the complexity of the real actuation, or we don't have much data about the actuator per se, in this case especially. So what we want to have is to mimic something which is representative of the final performance of the actuator. And so whatever is upstream to this, we are not able to really measure it and to model it properly. So it's more a functional model, not a model for developing really the system in the late stages. So that kind of model would then arrive later, probably from the supplier or from internal development of the system.
Great. Thank you very much again, Guido. We appreciate it. Guido will be available for other questions. We got to keep the agenda on time, but thank you very much.
Thanks.
I'd also like to acknowledge, too, and I forgot to do it in my introduction, but Guido and IDIADA also represent one of our premier platinum sponsors. So, Guido, thank you very much for that continued support.